Hey, Calculus, BC Calculus. It's Mr. Allinger here, and we're just going over the notes from 2.1. You should have read through the chapter and put in the notes that go along with this. And now I'm going to put in the answers just so you can check your work. So explaining what each one of these formulas means. This one here is talking about the secant line. So that's a secant line is connecting 2 points on a curve. So you'd have some curve, and I always tend to draw curves the same way. I apologize about my lack of creativity ahead of time. Like, that's what my generic curve looks like just about every time. And so you'd have some point C, and then you'd move over some delta x. That's the delta x in the formula. We're explaining this part right here. And so what are you finding? You're finding f of c plus delta x, and that would be the y value right here. So this distance is f of c plus delta x, and then minus f of c, which is this distance right here, would be f of c, right? The y value there. And so then when you find the difference between those, then you're finding this little difference between the two heights, and then you're dividing it by delta x, which is how far over you're going. This thing's just a slope, is all it is. And so this is the slope between 2 points. But another thing, and kind of tying back to chapter 1 and some stuff that we just kind of opened the door to a little bit, or we dipped our toes in the water of a little bit, is saying, well, what are we doing when we're finding slope? And what we're doing is we're finding the average rate of change. That you want to have that kind of solidly in your noggin, that the slope is the average rate of change. It's not exactly how fast you're changing here or how fast you're changing there, but it's the average between those two moments in time. Okay, but then when we go to this next one, it's pretty much the same drawing because it's f of c plus h. I switched the delta x's to h's. The first year I used delta x's, the first year I taught calculus, and then I was like, it's too many letters. It's too many symbols. There's two symbols. I only want one. And so I use h instead. It means the exact same thing. There's no difference. But now the difference is that we've added the limit as h goes to 0. And so this is saying, well, what if we made that delta x, that's h, remember, same thing. What if we made that infinitely small? But we kept c where it is. C hasn't changed, but now we moved it infinitely close. And so you'd have the same picture with c, but now delta x is a tiny, tiny little number. And I'll try to make about the same curve. And now you're finding the slope between those 2 points. And not only that, but it's the limit as h goes to 0, so it's even smaller. It's as you make this closer and closer to 0, then what are these slopes getting closer and closer to? And that's what the derivative is. So this is the instantaneous rate of change. The instantaneous rate of change at x equals c, because it's making the slope go tiny, 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 tinier until it's basically there's no difference between the point and the point after, but there's a tiny difference. And that's why limits were such an interesting creation. It was a way to say what would happen as you're getting closer to 0, in this case, without actually making it 0, which actually has an important meaning there. Could you just be a little quieter? And this is also known as, sorry, I just said someone else in the room. So, and this is known as the derivative of f of x at x equals c. That's what this is finding. Okay? So that's what that expression means, this thing, with the limit part of it. If you don't have the limit part, you find the average rate of change. If you have the limit part, you find the instantaneous rate of change. This one down here is the exact same thing. So this is also the derivative of f of x at x equals c. Well, why is this different? Really, the only reason we have this other version of it is that in some situations, it becomes easier to simplify the limit. And so it's helpful to have this second one. We call this the bread and butter definition of the derivative. And this one, it's kind of like bread and butter, but it's a little different. We call this one toast and jam. Okay? So there's bread and butter and there's toast and jam. those are not official. You can't put them on the AP. All right. And so it's the same thing. We've got the C. The only difference is instead of making the limit defined by how far you move over, instead we just say, well, let's make a point X here with the same idea, and now take that X point and make it infinitely close. It's the same idea. It's an instantaneous rate of change. It's a slope. It's just set up in a different way with a different limit. And that's the only difference between them. So now you're doing derivatives. Welcome to calculus if this is your first time. And so there's a bunch of notations, and there's a ton of different notations that you can use. The biggest ones that I'd want you to know were y prime. Y prime. You could say y prime of x, or you could just say y prime. Either one. Y prime of x just indicates what the variable is, like the difference of calling a function f or calling a function f of x. You're not saying something different there. We also can say f prime of x. These all mean the exact same thing here. You can also say that all those are variations on the notation that Newton used when Isaac Newton was developing this system. But simultaneously, while he was developing it on the continent, I think he was working for the French monarchy at the time. Gottfried Wilhelm Leibniz, I always like saying his whole name. He was developing the same basic idea, but just with some different ideas and some different notation, and he called it dy dx, the change in y over the change in x, the slope. But by calling it dy dx, he's talking about this instantaneously small slope, or infinitely small slope, excuse me. So that's what those notations, all those mean the same thing. I think the book also mentions this one. We use it very rarely. And in fact, we use it not at all, but every once in a while you see it show up somewhere. So you just need to recognize it. Okay, now we're going to work out this limit here of finding this derivative, finding the derivative function for f of x equals square root of x by finding this limit. So I'm going to pause it so I can write everything out, because it won't be interesting to watch me write. So I wrote the problem down in black with the function plugged in, and this is a situation we have over here that now we're not finding the derivative at one point. We're finding a function that will give us the derivative at any point. So that's the interesting thing, is that we can find the slope at one spot, but we can also, if we instead just leaving that spot as x, we can say, well, can we come up with a formula for what the derivative would be anywhere on this curve? And actually, to be honest, I was very sloppy here. I didn't bother trying to draw the curve itself. So the curve is square root x, which starts at 0, 0, and looks like this, right? And so we're finding the instantaneous slope by doing the limit. We're finding the instantaneous rate of change between x and this point that's a little bit later that we make infinitely close. And so we're finding a formula for what the derivative is anywhere on square root of x. So we're finding, rather than finding what is the slope at 2, we're finding what is the slope everywhere, because we'll have a formula for it. So derivative can be used in two senses. It can be the derivative function, which is everywhere, or it can be the derivative just at a point. And it's the same word for both. You just say derivative. So the original problem was in black there is that square root, or that limit. And if you plug in 0, first thing you do when you have a limit, plug in 0, you get 0 on the top, you get 0 on the bottom. 0 over 0, which means you have more work to do. So I multiplied the top and bottom by the conjugate. This is just a trick to use for radical ones. And the numerator is a difference of two squares, so you can FOIL it, and you end up getting x plus h. It's the first one squared minus the second one squared. So it's x plus h, and then minus x, because the square root cancels out when you square it. And the denominator I didn't distribute. A lot of people will distribute it, and then they'll get confused. The whole point is to cancel out this h. Like this h that's there, that's our problem. When we plug in 0, that makes our denominator 0, and we don't like that. So we're hoping to cancel that h out at some point, which means keep it separate. Don't distribute it, because then that's going to make it harder to see. You simplify the top, and it's just h, and there's h in the bottom, so you can cancel them out. And now you can plug in 0, and it's 1 over square root x plus square root x, which is 1 over 2 root x. And that's the answer. That's the limit. And we just found a formula for what the slope is anywhere on square root of x. So if you go to x equals 1, if you went to x equals 1 early on the curve, the slope would be 1/2. This is not to scale. I didn't bother trying to make this perfect. If you go to x equals 4, so a little bit later, suppose that was 1, but this is 4, we can say, oh, I can tell the derivative should be smaller because the slope is smaller, right? The tilt of the graph is smaller. Plug in 4 and you get 1 over 2 times 2, you get 1 over 4 as an answer. Go out to ... go out to 100, way the heck out there, and it's 1 over 2 root 100, which is 1 over 20. Then when you go out to 100, then it's really, really flat. It's really, really close to 0. All I'm showing is by plugging in these numbers, I can see that the derivative is matching what I can see with the picture. It's like, oh yeah, it should be getting smaller and smaller and smaller as x gets bigger, and that's what it's doing. So you just learned your first derivative. What does differentiable mean? Differentiable, it means smooth. So we had continuous in chapter 1, which meant connected. You could draw it with your pen, and you never have to lift your pen. But differentiable is something extra. It's not only can you draw it without lifting your pen, but it's smooth. It doesn't have any abrupt changes. What are examples of functions that are not differentiable that you've seen? Well, one is if it's discontinuous, then it's not differentiable because it's got to be smooth and connected all the way through. Sorry, somebody's passing by. What are some other examples? One is if you don't have a limit, then remember it's not continuous. So you remember like the one from chapter 1 where it's infinitely many oscillations but not getting closer to 0. That would not be differentiable. One of the most common ones to think about is like an absolute value graph. And at that point right there, it's not differentiable because it's not smooth. It abruptly changes. And you might say, well, why isn't it differentiable? If you tried to make the limit, it wouldn't exist. So the idea, and I guess, sorry, I was looking at the next question too. So so an example is if you made h positive so that you went over a little bit and you found the slope on y equals square root of x, absolute value x, sorry. Then you can see that if you made h over here and you found the slope, the secant line, slope of that line, you'd get 1 every time because that's the tilt of the absolute value graph. And as h goes to 0, you'd always be getting 1. But what if h was a negative number? Because when we say h goes to 0, h could be positive or negative. Either way, you can get closer to 0. If h was a negative number and you found that slope, you get negative 1. So on one side, you get 1. On one side, you get negative 1. This limit, I'm just going back to the limit there. That limit doesn't exist because if h is approaching 0 from the right, you get one thing. As h approaches from the left, you get something totally different. The limit doesn't exist, therefore it's not differentiable. And that was the big thing here so continuous is you can draw without lifting. I know it just said that in the paragraph, but I'm just trying to make the notes really good. And differentiable would be the same and smooth. That's just what the idea. So there's the official idea of it, that the limit exists. If that limit exists, it's differentiable. But then there's the just sort of basic idea of it so that you can easily look at something and say whether it's differentiable. If it's differentiable if it's continuous and smooth with no abrupt changes to the slope. Okay, that's 2.1, the intro, and we'll have more next time. I decided to add a little more. I just want to summarize because I have a minute left here. So big idea on this is we're getting the idea of what derivatives are. Instantaneous rate of change, and we can find this by making these limits. The big thing you want to have are those two different versions of the derivative. You definitely want to know both of those, and we'll see examples where mostly you have to be able to recognize what that expression is and be able to set one of those things up. I'll just say that for right now. There's going to be a lot of notation. I showed an example of finding a derivative function, and then the meaning of differentiable. That's what this 2.1 mostly is about. We'll see a little bit more next time. That's it.